Okay, this is the practice test for Chapter 2, and the first problem says the number of bacteria in a refrigerated food product is given by this function here, and capital T is the temperature of the food, and N is the number of bacteria, and it says when the food is removed from the refrigerator, the temperature is given by this function here, capital T of little t. Capital T stands for temperature, and little t stands for the amount of time in hours that the food has been out of the refrigerator. So it says to write a composite function n of capital T of little t. So to do this, we substitute the 2t plus 1 n for the capital T. So that would be 25 times parentheses 2t plus 1, that gets squared, minus 50 times the 2t plus 1 plus 300. Now to simplify this, you could either FOIL this together by hand and simplify it, or you could go to the poly sheet. You go to the poly sheet, and I'm on the poly sheet right now, scrolled all the way down to the bottom, and I've put in my coefficients here, and I end up with this quadratic equation right here. So my simplified version of this would be n of capital T of little t equals 100t squared plus 275. Okay, that's it simplified. Now it says find when the bacteria count reaches 750. So what I would do is go to the quadratic sheet and put in my coefficients for my simplified polynomial there, which is 100, a 0, and a 275, and then put the 750 in for y, and I get two answers. So these are the two times in which the bacteria count would reach 750. Okay, for problem number 2, it says the value of the Dow Jones can be modeled by this equation with this restricted domain. D is the value of the Dow Jones, and T is measured in years, and T equals 0 is the year 2000. It says use the model to find the months in which the Dow Jones is 8,000. Well, this is a cubic equation, so I went to the cubic sheet. Here's the cubic sheet, and I put in my coefficients for A, B, C, and D. And then I wanted to know when the value was 8,000, so down here for y, I typed in 8,000, hit enter, and clicked the Find Solution button, and I get these years. So it would be year 2001.5, year 2004.4, and the year 2012.02 approximately. Now part B said, according to the cubic model, what is the highest the Dow Jones will ever be within a restricted domain of 1 to 15? Okay, so using that cubic model, restricted domain of 1 to 15, and want to know what is the highest it will ever be. Well, down here we're looking at this area where it says absolute max, so your answer is 8411.55, and that will happen in the year 2009.12. And then part C wanted us to change our restricted domain to be -2 to 15. Before I do that, I'll confirm that this last answer is correct by setting my viewing window to be the same as my restricted domain, 1 to 15. And if I look, I can see the maximum is this little peak right here, which appears to be somewhere between 8 and 10. So that is, the 9 makes sense for the number of years. And the height is up here, above 8,000. So that seems to be right. Now for the next part, it was between with a domain of going from -2 to 15. So I'll set the domain that way. And it says that this one is asking again the maximum, and the maximum occurs at year -2, which is the year 1998, and the value would be 9,280. And we can set our viewing window to be the same to compare it, -2 to 15. And if we do that and look at the graph, we can see that it's higher at -2 than it was anyplace else. So the local max is not the absolute max on this restricted domain. Let's go to problem 3, and on problem 3 it gives you another equation for the value of the Dow Jones, which is a fourth power equation with this restricted equation, with this restricted domain going from -2 to 15. This is a quartic equation right here. So we'll go to the quartic sheet, and I put in my coefficients, and same thing, go down here and put in your 8,000, which is what they wanted you to do, and it will tell you the years in which the value of the Dow Jones was 8,000. Remember to type in the number, hit enter, and click the Find Solutions. Part B of this problem wanted you to find the lowest the Dow Jones will be within a restricted domain of -2 to 15. So put in your restricted domain here, and the lowest is actually right here, a value of 7860.61, and that would be 2.716 years after the year 2000. And we can confirm that on the graph as well, that the lowest is at 2.7, and you can see this spot here is a little bit lower, and that's about 2 point something. And it's hard to tell by just looking at the graph. That's why you need this area right here. Now part C says according to the fourth power model, the Cordic model, what is the maximum the Dow Jones will be from the year 2001 to the year 2024, 1 to 24? Well, set your restricted domain to go from 1 to 24, and you could set your viewing window to be the same, 1 to 24. And we're again looking for the maximum now, and the maximum occurred out here at year 24, year 2024, with a value of 32,209. Don't believe that because that's long-term extrapolation there. Now part D says same problem as the previous problem, but change the domain to be 1 to 16. If we change it from 1 to 16, here I'll show you this graph here before I change it. With 1 to 24, see the graph is done doing all of its little mins and maxes, and now it's just going to go up from here out. So that's why the endpoint was the highest. But if we go 1 to 16, and we're looking for the maximum, it's at year 8.56, and this is the value. And let me confirm that here by typing in 16. Let me scroll over so you can see what happens to the graph when I hit enter. So I'm looking from, here we go. So now we're looking at this section of the graph, and if you look, the maximum did occur right here, it'd be around year 9 point something, and it's around 8,500. And here it is, exactly 8.56, and it's 84.96. And then again it says 0 to 16. Well, if we go from 0 to 16, it tells me that my maximum now occurs at year 0. Well, watch what happens to this graph if we include 0 in it. Well, now it's shot up higher, and it is higher at 0 than it is anyplace else in this graph. So the maximum occurred at the year 2000 on this restricted domain, and it was at a value of 8703. And one thing I wanted to remind you of is don't forget to click the max mins button on the Cordic sheet. You have to do that before it will get you your local max or mins. So I had already done that. Now let's go on to the next problem, which is Game Commission introduces 40 new deer into a newly acquired state game land. The population of the herd is given by this rational function here, and I can tell it's rational because there is a t in the denominator. Where t is time in years, what is the limiting size of the herd as time progresses? We'll need to simplify this a little bit by distributing the 10 through to get 30 plus, let's see, that'd be 30 plus 20t. 30 plus 20t over this, and so this is a rational expression, so let's go to your rational sheet. The coefficients on the numerator were 30 and 20, and on the denominator the coefficients were 0.05 and 1. 0.05 because it's 0.05t, that would be your C2. Now it asks what's the limiting size of the herd as time progresses. Well, you can see as time progresses, I got my viewing window to be 0 to 1,000 here, and it's leveling off to what? Well, about 600. Well, that's the horizontal asymptote, and that's what we're looking for on this problem is the horizontal asymptote. So the answer to this problem is 600. Okay, on problem 5, it says the cost in dollars of a new cancer-fighting medicine can be modeled by this equation right here, where C is the cost of a unit of this medicine, and X is the number of units that can be produced per day. According to this model, what does the cost approach as the number of units produced gets large? Well, as X gets larger and larger, I put in my coefficients here, by the way. There's 20X plus 2 over X minus 1. And then as X gets larger and larger, it's the height or the cost is leveling off to $20. Again, that's a horizontal asymptote question, and that's the answer to part A. In part B, it says, according to this model, what does the cost approach as the number of units produced approach only 1 per day? Well, if I put 1 in here for X, I get infinity, and the reason is because there's a vertical asymptote at 1. And again, you have to click this button to get your vertical asymptotes, and it tells me that there's a vertical asymptote at 1. So that's why the cost is approaching infinity. You may not be able to see it well unless we go just near that vertical asymptote. You can see it shooting straight up there at that area. On problem 6, it says the following information is gathered on the growth of the internet. Here's the years, and here's the number of internet domain names. Let t equal 0 be 1990. So it says find the power function of the best fit. And so I went to the power function sheet. I put in my data, which actually goes from 2 to 7 because year 0 was 1990. So 2 through 7, and here's my y values. I put in my data and I click the get equation from data points, and here's my equation, or you can see it right here better, and that's my power equation. Then part B says when will there be 4 million internet domain names? So I put 4 million in for y, and I got 9.94.